This is going to be a video on just strictly on your KEQ calculations. So when you start your KEQ calculations, it's very important that you're not just looking at the number, but actually reading the question, understand what the question is asking for. So in order to begin, understand that, remember, KEQ or KC, you're looking at the ratio between your products divided by the reactants. A lot of students get this confused because they automatically just find all the numbers in the question and plug this in. But the only difference is that you can't use this automatically in some questions, because this equation is for concentration of products at equilibrium and divided by the concentration of reactants at equilibrium. If you look at this question, it's not at equilibrium. Reactants A and B are mixed in a 1 liter container, each with initial amounts. That means that that's before the reaction actually got started, of 0.8 moles. They react to produce C and D. So then here's the reaction at equilibrium. So then now you're given the equilibrium amounts of C and D, which is 0.6 molar, and you're asked to find KEQ. So in order to tackle this problem, there's a technique called the ice chart, which is basically a table to organize where your concentration is heading, or how much you have starting at the initial amounts and how much you have at the equilibrium amounts. How you organize this is that you're going to put ICE, I for initial, C for the change, and E at equilibrium. And then at the top, you're going to write all your reacting species, which is going to be your A. I'm just going to write my table like this. And then B, this is going to react and form your C and D. You actually don't really need the middle column. So this is your ice chart. So then you're going to use this ice chart and just fill this in all the things that you're given. So you're given A and B with 0.8 moles. We can't use moles, we have to use molarity. So to get the molarity, we're going to go 0.8. What's my volume? I have 1 liter conveniently, so that's just divided by 1. So I start off with 0.8 molar for A and for B. Because this is at the initial, we don't have any of the products, so that's 0 and 0 molarity. So the next thing that we know is at equilibrium, the amounts of C and D are found 0.6. So we know at equilibrium, so we're going to put that under the E, and for C and D, we're going to put 0.6 molar. This is still within the 1 liter container, so 0.6 molar. So this is all that I can put into this table. The next step is we have to see what's the change. So starting at your products, we started from 0 and we actually gained 0.6. That means that it's going to be a plus 6 molar here and a plus 6 molar here. It's a positive because you're in the product, so your reactants actually gain or reacted to gain more products, which is your positive sign. So then we have to calculate, well, if 0.6 actually got created for C and 0.6 got created for D, how is that for B and A? And in order to calculate for here, we need to use stoichiometry. You have to use stoich here. And conveniently enough, you have in this reaction, A plus B plus gives you yield C and D. There's only 1, 1, 1, and 1. That means the ratio is just 1 to 1 to 1 to 1, which is very convenient that you'll get 0.6 and 0.6. And since this is your reactants, you're going to have a negative sign and a negative sign because you're taken away from that. That's the amount of moles that gets used up. So you just do your basic math here, 0.8 subtract 0.6. So at equilibrium, so this is at equilibrium, you get 0.2, and at equilibrium, you get 0.2. So finally, once you have established this row at equilibrium, you can use your KEQ formula, which is going to be your C times the concentration D divided by concentration A times concentration B, and you just substitute all these numbers, 0.6 times 0.6 divided by 0.2 times 0.2, and this will give you an answer of, so let me just punch this in, should be what, 0.36 divided by 0.4, which 0.04, which gives you a KEQ of 9. So once you have established this, it's a good idea not just to stop at the answer, but actually what does this 9 represent? And since this is greater than 1, that means that you're going to get more products than your reactants. Your forward reaction is actually favored than your reverse reaction. So this is the first type of problem. This is using the ICE table and using stoichiometry just in your change row to see how much change is found in your other sort of reacting species. So that's the first type of question. So this is another question involving KEQ and the ICE table. So this one is very similar to the previous one. If you want to just kind of stop here and try it out and see if your answer is the same as mine. But here it goes. In a lab investigation, 2 moles of sulfur dioxide and 3 moles of nitrogen dioxide are mixed in a 2-liter container. We need to know that. Once equilibrium is reached, the container is found to have 0.5 moles of sulfur trioxide. So first thing I would like to do is write out your reactions. So sulfur dioxide and nitrogen dioxide. This will give me an equilibrium reaction, give me sulfur trioxide. I think there's something missing here. I think we're missing a nitrogen monoxide. These are all going to be gas form, so all of these ones will take into account in my law of mass action equation. And I'm just going to change all these and write into, well, I guess I'll just put it into my ICE table. So here's my ICE. And I know that this is in a 2-liter container, so I need to divide all these moles into 2 to give me my concentration. So let's start with my initial. Sulfur dioxide has 2 molar divided by 2 liters, that's going to be 1.0 molarity. Nitrogen dioxide, 3 divided by 2, that's going to be 1.5 molarity. And this is initial, so it's going to be 0 for the products. And next thing is, once equilibrium is reached, the container is found to have a 0.5 moles of sulfur trioxide. That means it's going to have a 0.25 molar because I divide by 2 of the container. So now the next step is to fill in the rest. The thing here is, the only thing I know is the change, because at equilibrium I started with 0, right? And then once all the reactants reacted, I gained 0.25. That means I gained a 0.25 molar. So the next thing I want to see is, I want to see if my reaction is balanced, because I actually didn't check for balancing, because the molarity or the molar coefficients actually matter. I have 1 sulfur, that's good. I have 4 oxygens. Okay, so this is balanced, 1 nitrogen, 1 nitrogen. So that's good, because then now for the change, I'm going to use stoichiometry using the molar coefficients. But since this is a 1 to 1 to 1 to 1 ratio, this is going to be plus 0.25, minus 0.25, minus 0.25. That's really good. So then I can add this at equilibrium. I actually have 0.25 of your nitrogen monoxide. This is going to be subtracted, so it's going to have 1.25 molarity, and this is going to have 0.75 molarity. So once I have established my equilibrium row, this is not done yet, because then I need to write my Kc is equal to 0.25. This is my products divided by my reactants, so 0.75 times 1.25. And you can sort of see that this is probably going to favor reactants because my denominator is bigger. I have more of my reactants at equilibrium. So I'm going to finish the math here. So 0.25 times 0.25, that gives me a answer of 0.0625 divided by 0.75 times 1.25, which gives me 0.9375. So the final answer is 0.0625 divided by 0.9375. That gives me a final answer of 0.0667. So this is my K. Well, actually, you don't even have units because it's the constant. This is my Kc, this is my equilibrium constant, and this is less than 1. that means that it will favor the reactants. So after all this is mixed, you actually have more of the reactants than the product. So this is another example. Hopefully you're starting to understand how to use this ICE table. So the next one, next question we're going to do is going to be the little tricky one. So stay tuned for that. This example is probably the most complicated because it actually involves the use of an X or algebra to solve for it. This is the type where you're given just the initial concentration and also the KEQ number, but you are now asked to not solve for the KEQ but the concentrations at equilibrium. So in this question, in a lab, you have 0.5 moles of hydrogen, 0.5 of iodine are placed in a 1 liter flask. The equilibrium constant now, so you have your KEQ, this is at 54.3 at this temperature. Calculate the concentration of HI and HI at equilibrium. So let's write this. H2 plus I2, this is going to give me a reaction of HI. I need to check if this is balanced first because remember the change row, I need stoichiometry. So I have 2 here, and I just need to put that as a 2. So the next thing I'm going to use is going to put this all into ICE table and see what I have. So I start off with 0.5 hydrogen, moles of that, but since I have 1 liter flask, that's very convenient because I have 0.5 molarity, 0.5 molar. And then iodine, I have 0.5 molar as well. This is 0 because that's my products at initial. And you notice that that's all that you're given. You don't have anything else, and I can't assume that all my reactants are going to be used up because you don't know that. You don't know if all your reactants will be used up or at equilibrium you have more reactants in products because we haven't calculated that yet. So we can't put 0.5 at equilibrium. However, we can actually have to now put in an algebra or an X. And since that you know that you're going to gain something in your products, you're going to have a plus sign. And because I have 2 for molar coefficient, I'm going to gain 2x. So this x is the unknown that you're going to gain, and the 2 is because you have 2 molar, so that's your 2 times ratio of the other one. And because of this, then we can calculate, or actually just calculate for the change for the reacting species. And since this one has a 2 of molar coefficient, all these ones have 1, right? So this is going to be minus x and minus x. So with that, then we can actually just put all this in equilibrium because 0 plus 2x is just plus 2x. This is just going to be 0.5 minus x and 0.5 minus x. So now we have established our equilibrium even though we don't have the numbers. The good thing is that we actually have our KEQ number, right? Because we have KEQ. This is going to be equal to my HI squared divided by H2 times I2. So that's my law of mass action expression, and I'm just going to substitute these numbers in, or algebra. So 2x squared divided by 0.5 minus x times 0.5 minus x. And you can notice that this 0.5 minus x and 0.5 minus x are multiplied to each other, so we can actually put that as 0.5 minus x squared. That's what that is. And the top part is going to be 2x squared as well. I didn't want to do 4x squared because of this reason. KEQ is 54.3. So the reason why I don't want to change all this is that because the numerator is square, the denominator is square, so why not take the square root of both sides to get rid of that? So let's get rid of that. I'm just going to scroll the page down. So what happens is that the square root and the squares will cancel, giving me a 2x divided by 0.5 minus x. And you can probably see where this is going. And the square root of 54.3 is 7.37. So then I need to isolate x, cross multiply this. So 7.37 times 0.5 minus x is equal to 2x. Okay, so far so good. Distribute this. So 7.37 times 0.5 is equal to 3.68 minus, this is multiplied by x, so I get 7.37x is equal to 2x. I'm not done yet because I need to isolate x, and since I have x here and x here, I need to move them onto one side, so I add 7.37x to both sides just to get rid of it from the left side. This will cancel. 3.68 is equal to 9.37x. And you can see that the last step is coming up pretty soon because we just need to divide by 9.37, 9.37, which cancel this all out, is leaving me with x, and that number on the left is 0.39, and this is x. And how we calculate for the concentration is that now we have to look back up. What does x represent? Well, HI is 2x, so we can actually calculate what 2HI or HI is. Whoop, HI. HI is 2x, so then 2 times 0.39 is 7.8. 0.78. What am I talking about? 0.78. That's the concentration of my HI. And my H2 and I2, this is where they had 0.500 minus x, which is 0.500 minus 0.39. This will give me an answer of 0.11 molarity. So this is for the concentration of H2 at equilibrium. This is going to be the concentration of I2 at equilibrium. So just to recap, if you got a little bit lost here, this one you're asked to find the concentrations instead of KEQ. You're only given the initial amounts, and because of that reason we need to just put an algebra in there, an x, and we put that into the change row because that's what you're gaining in the products. And why I have this too, because of the molar coefficient, and these two reactants have just one, so instead of having two, I have one. So I gain, so I have positive, I have minus for the reactants because I'm losing. And then once I have that, I can establish my equilibrium row because this is just going to be plus 2x. This is my 0.5, what I started off with, minus what I used up to make the products, which is x. Bam. And then once I have the equilibrium row, I'm going to put this into my law of mass action expression. And I have this 2x squared, and then the bottom number, this is usually going to be squared. If we're not, there is an example where you actually do have to use quadratic, but this one doesn't. And then take the square root and then solve for x. Once you solve for x, you just substitute this x number back into your original amount, which is 2x. So your x, HI is 0.78 molar, H2 and I2, they're 0.11 molar. So this is the most difficult one out of all your ice chart calculations, but practice it. You can stop and replay this. Hopefully this video has helped you calculate this. So thanks for watching.